So today we have a great pleasure to have Chen Yu-Ching from UIUC to speak. And Yu-Ching, he was a undergraduate student from NTU Physics, and now he is a PhD student at the UIUC Astronomy Department, and he will graduate next year, pretty soon. So in this colloquium, he will talk about searching for binary supermassive black hole in the astronomical survey, and he is working with Chen and Liu-Ching at the UIUC. So let's welcome Yu-Ching's talk.
Thanks, Ken. So hello everyone, I'm Tony Chen. So I'm the 4th year graduate student at University of Illinois. And as Ken mentioned, I work with Professors Liu-Ching and Professor Shen on binary AGN and dual AGN. And today I'm happy to present some results of our ongoing projects. So the title is Searching Binary Supermassive Black Hole in Astronomical Surveys. So this is the outline of the talk. First, I will make a brief introduction, and then I will talk about two projects which I have been working on. The first one is periodically variable quasars using the dark energy survey and the Sloan digital sky survey. So those periodical quasars are possible supermassive binary black holes. And on the second project, I will also talk about a new astrometric technique trying to find the unresolved dual AGN or off-nucleus AGN. And in the end, I will give you like some takeaway points. Okay, a brief introduction. Why do we care about dual AGN or binary AGN? Okay, so first I will, because most of the nearby galaxies, they harbor the supermassive black hole, such as our galaxy, we have a big massive black hole in our galaxy centers. And we also find on the distant universe, there are lots of bright, for example, the quasars or AGN. And on the other hand, we also know in the simulation, the universe shows a hierarchical merger structure in their simulation. So those two facts will lead to, like, we expect to see the binary supermassive black hole in the end. However, finding those supermassive binary black hole is not as easy as we thought, because there are still lots of problems we haven't thought about. For example, the final parsec problem. So the final parsec problem is the problem when two binary black holes, they are at the parsec scale. They run out of the star, which they can shrink their orbit through the three-body interaction. However, they are not close enough to emit the gravitational wave, so they will stall at the parsec scale, and they cannot like shrink their orbit. Also, like finding those binary supermassive black hole at high redshift, we can understand the redshift dependence of different kind of dual AGN. And we can also know like what's the occurrence rate of those binaries. For example, like what's the fraction of the binary among the quasars. So here I'm showing you a brief physical scale and the angular scale and the corresponding angular scale on this plot. So on the kiloparsec scale, because it's scene limited, so we only have tens to hundreds of confirmed cases at lower redshift, which by lower redshift, I mean redshift less than 0.1. And there is only like one confirmed case like at redshift higher than 0.5, which at the 2 parsec scale. However, if we go down to more smaller separation, which is sub-kiloparsec scale, we only have one confirmed case at 7 parsec, So we want to use other space telescope or the radio interferometer such as VLBA or VOA to find those sub-kiloparsec scale dual AGNs. If we go into the more smaller scale, for example, the sub-parsec scale, there is no like direct method or direct imaging we can use to find the dual core because they are too close, which may be smaller than micro arcsecond. So there is no like confirmed cases, and we need to rely on the indirect method. So speaking of the sub-parsec scale supermassive binary black holes, yes, as I said, they cannot be resolved even with the VLBI. And so we need to rely on some indirect method, such as the periodic signal in the light curve. So as you think, if the binary are in the, for example, the circular orbit, the Doppler boosting will like change their brightness in their light curve. So you will expect to see some sinusoidal signal in their light curve. Or in some hydrodynamical simulation, they also show some modulation in their brightness. So we can use those periodic signal in the quasar's light curve to try to find some possible binary supermassive black hole. And in my first project, I will talk about this more. There are still some other methods. For example, we can see if there is, we can take the SED of quasars and see if there is some significant deficit in their SED, because if you have a binary, it will create some gap between the circumbinary disk and their mini disk, such as the second panel here. And those gaps will contribute to the deficit in their UV to optical spectra. And the other method is to try to search the broad emission line shift. If two binary are more far away, their broad line region still like exists in individual cores. You will expect to see their broad emission line will shift as they move. So on the larger scale, such as the sub-kiloparsec scale, there are lots of progress have been made for the low redshift dual AGN. So the plot here, I'm showing you on the x-axis is a redshift, and on the y-axis is a projected separation, and each dot are the confirmed cases of each dual AGN. So as you can see, on the left side, there are lots of progress. We have found lots of many dual AGN at low redshift down to around 1 kiloparsec. However, at high redshift, because of the seeing, we can only reach down to the 1 arcsecond, which corresponds to roughly 10 kiloparsec. So at high redshift of things, at high redshift, there is still lots of unexplored territory here. We can try to find the dual AGN at this scale, and we need to. My second part of the talk will focus on this region, and we will use a new astrometric technique to search the unresolved dual AGN. Okay, let's move to the first project, the periodic variables quasars. And this is also a large collaboration. We work with different peoples on this project. So in this project, we want to combine the dark energy survey and the Sloan digital sky survey to search a possible periodic signal in the quasar's light curve. And before we move to the data, I want to briefly introduce the survey we use. The first one is a dark age survey. It is a 6-year multi-band imaging survey from 2013 to 2019. And it uses a 4-meter telescope in Chile. And it has a large field of view. And besides the wide field survey, it also has 10 supernova fields, which has a high cadence. With cadence of 6 days, we can use those data to make a beautiful light curves. And the dark age survey has a 4.6 square degree overlapping region with the Sloan digital sky survey stripe 82. So we use the quasars in this overlapping region to make the 20 years long light curve. And the Sloan digital sky survey, I believe many of you have already known this survey. And it is so in stripe 82, it has a 9-year multi-band imaging survey. And yes. So how do we select our sample? As I mentioned, we use the spectroscopical confirmed quasars in the overlapping region of the DES supernova fields and the SDSS stripe 82. We select the quasar with only sufficient epochs, and also we use some flag to ensure there is no artifact in our measurement. And our final sample has 625 quasars. It's a small sample, I know, but because the overlapping region is also very small. But the time baseline is a very important thing, and I will talk about it later. So here I'm showing you the light curve, one example light curve of our quasars. On the left-hand side is the measurement from SDSS, and on the right-hand side is the measurement from DES. And as you can see, our light curve spans roughly 20 years, so which can help us find some important or significant periodic signal, because quasar also has its own variability in their light curve. So having enough time baseline is crucial to exclude some false positive from the quasar's intrinsic signal. So how do we select our candidates? First, we use the generalized Lumskargo periodogram. The Lumskargo periodogram is a a popular tool to find the periodic signal in the uneven sample data. And the generalized means we allow it to shift, has some shift in the 0 point. And we select those good candidates using more than 99.74% in at least 2 bands. So the 99.74% here is calculated from we feed the DRW model to the quasars. So DRW model is a popular model which to describe the quasar's light curve. So we generate the whole bunch of the marked light curve using the DRW quasars and use it to calculate our significant level. So the higher significant level means is deviate from the periodic signal is deviate from the pure DRW model, which means the sinusoidal signal may not be generated by the DRW, but it will be maybe a true periodic signal. And on the second criteria, we also select use the signal to noise ratio, which signal is the amplitude of the periodic signal, and the noise is the residual after subtracting the periodic signal. And we also check our results with other methods, for example, the autocorrelation function. And the result is consistent, the period is consistent with the period found in the Lumskargo periodogram. So here is our results, and on the right hand side, I'm showing like one candidate, the light curve of one candidate. As you can see, the light curve span more than 5 cycles, which means this this periodic signal might be significant, and we have found 5 strong candidates out of 600 quasars. And we also calculate the false alarm probability using the other, for example, the look elsewhere effect, and we find up to 1/3 of those candidates might be false positive, but still we should have like some good candidates. Because those quasars are spectroscopy confirmed quasars, so they have the spectrum. We can use some emission light, for example, carbon-4 or magnesium-2, to derive the single epoch virial black hole mass. And those black hole, their mass are around like 10 to the 8.5 to 10 to the 9 solar mass. If they are the real binary, if the gravitational in spiral time is around like 10 to the 4 to 10 to the 5 years, so they will not merge immediately, and the separation is around milliparsec. Because our light curve are multi-band, we can also test the Doppler boost hypothesis to see if the periodic signal are from the Doppler boosting or from more complicated mechanism. So the Doppler boost hypothesis will predict the A here is the amplitude of our sine signal, and the alpha here is the spectral index estimated from the Sloan spectrum. So we have the multi-band data, so we can make the plot like this to see if our data are deviate from the prediction from the Doppler boosting. And we find there are like more than 2 sigma deviation from the theoretical prediction from the Doppler boosting for the 4 candidates. And for the rest candidates, the parameter space is limited, so it's also highly unlikely this candidate will be the periodic signal will due to the Doppler boosting. And we can also compare our sample with the previous surveys. So on the right hand side, I'm showing our candidates on the redshift versus the black hole mass plot, and also the optical magnitude. As you can see, our candidates here, the red star here, they are more fainter than those previous candidates found from the previous surveys. For example, the Catalina surveys, and also the CRTS, PTF, and Pan-STAR surveys. So our the magnitude is more fainter, and the black hole mass is also smaller at higher redshift. So our detection rate of our survey is 4 to 80 times higher than the previous survey, but we're still not sure what's the discrepancy between 2 detection rate, because different people, they use different selection criteria. But we have the better like data quality, and also the longer time baseline, which is around 20 years, and better photometry sensitivity down to the R-band to 23rd. And our candidates, so we might be probing different quasar population for our candidates, because at high redshift. Because at high redshift, as we know, like at redshift 2, there is a cosmic high noon, which the star formation rate peak, and also we have different kind of lots of quasar activity at higher redshift. So it might be a hint that we are probing different quasar population. However, the binary scenario cannot be the only true interpretation, right? Because as we see, like the periodic signal, it might be due to other mechanism or other like possibilities. So we need to discuss other physical interpretation for our candidates. And the first one is the precession radial jets. However, as we look at the radial imaging of our candidates, we find they are not quasars, or their radial loudness is very small. So their optical emission is not dominant from the radial jets, and the precessing radial jet scenario is highly unlikely. However, we still need a deep radial observation to exclude this scenario more. So we have the ongoing VOA observation for 3 candidates. And the second one is the tilted accretion disk. So if your accretion disk is wrapped or the tilted, and you might be seeing like some periodic signal or like some periodic signal in their light curve. However, the amount of the continuum obstruction is too large to explain our variability amplitude. As you can see, like our amplitude is around, let's see, 20 or 30% of our brightness. So it's hard to explain this scenario using the tilted accretion disk. And the third scenario is the QPO, the quasi-periodic oscillation, which often seen in the X-ray binary. So our timescale of our candidates are broadly consistent with the scale-up AGN version of the QPO, because most of the QPO found at like smaller black hole mass, but our timescale is consistent with the scale-up AGN version of QPO. So we still need the continuous monitoring to see if the periodic signal are from QPO. However, because the QPO often shows the drift in their amplitude and the phase, but if it's a real binary, it will not show the drift in and the drift in the amplitude and the phase. So here is our current status. We have published our results on monthly notice. So if you are interested, you can look at our paper. And we plan to use more quasar samples. For example, we want to use the photometrically selected quasar sample to get more quasars and have more like statistical important sample. And we also have the follow-up daycan observation on the supernova fields, which can extend our time baseline, and also we can bridge the gap between the DES, the Dark Energy Survey, and LSST. LSST will be start, I think, first like next year if everything is going well. So we will have 10 more year light curve for our candidates and also the new sample. And we also, as I mentioned before, we have the deep radio imaging, ongoing radio imaging to reject the precessing radial jet scenario. And 3 of our candidates have been observed with VOA, so stay tuned. Okay, so before I go into the second project, is there any questions for the first project? Okay, good. So let's move to the second one. So the second project, we want to use a new astrometric technique to find the unresolved dual AGN. So we call this project the vastrometry. So vastrometry is the combination of the variability and astrometry. So we want to use the variability in quasars and combine it with the astrometry technique to find the unresolved of nucleus and dual AGN. And this is also a large collaboration with Xiangzhi and Nadia at Johns Hopkins. So in this project, first I want to talk about the principle of this project. And as we know, in most of the astronomical survey, the astrometry precision usually is much, much smaller than our spatial resolution or angular resolution. So if there are two AGN, they are unresolved, which is like the panel A here, two black hole or two AGN, they are within the spatial resolution, so they are unresolved. And the red cross here is the central you measure for this unresolved source. If the right black hole are brighter, the central you measure will shift to the right. And if the left black hole are brighter, you should expect the central will shift to the left. So because if two black hole or two AGN, they emit not coherent emission, it should like give you more like the central jitter. You will expect if you measure it several times, you should expect to see the central will shift along two black hole, or they will have the high astrometry noise. So if there is an unresolved dual AGN or off nucleus AGN or lens AGN, and it will like we can use this technique to search if there is a possible unresolved dual AGN, and the high astrometric noise will be possible unresolved extended source. And here I want to introduce Gaia. So Gaia is a old sky survey, and which is designed for precise astrometry. So which is very good because we need a precise astrometry. And it was launched at 2013 and expect to operate until 2022. And it has a DR2 available in 2018. So because it's a old sky survey, so it observed lots of sources, more than 1.3 billion sources, with a limiting magnitude down to the G-band magnitude 21. And it has an excellent theoretical angular resolution, which is 0.12 arcsecond. Although like in DR2, the resolving power is not as good as the theoretical, but it's still good. So it's down to like 0.5 arcsecond. So usually the ground-based telescope, the seeing of the ground-based telescope is around 1 arcsecond. So we can use this Gaia survey to find the unresolved dual AGN, and as I said, the astrometry uncertainty is around 0.7 milliardsecond, so which is 1,000 times better than is like angular resolution. So which is good because we need the very accurate astrometry measurement. So it's excellent for testing the astrometry technique. Okay, so we have selected like some candidates using the Gaia surveys, and we we want to check if our technique is useful, or is just our thought. So we follow up 150 candidates using Hubble Space Telescope. So the angular resolution of Hubble is around 0.1. So we can use it to check if our candidates are real binary, real dual AGN, or is just some instrument noise or some other artifact. So we follow up 150 candidates. So those candidates are selected from different, most of them are spectroscopy confirmed quasars, and some of them are photometrically selected quasars. And we select two categories. The first one is they are unresolved with Gaia. So they only have one like one sources in Gaia, but they have the high astrometric noise. And we also select like some Gaia resolved sources just for like safety check. And we find, so on the bottom panel, we show like how many targets we propose, how many are observed, and like how many turn out to be multiple. So we find like the success rate of our astrometry technique is like very high. 14 out of 50 of the candidates turn out to be multiple, and I will show you the images in the next panel. So we are glad our technique worked, because if it doesn't work, we will be in trouble. So here I'm showing you the dual band HST images of like some candidates. And so the green cross here are the Gaia detection. And as you can see, like some of the images, there is only like one Gaia detection. However, our technique do find, like our HST follow-up images do shows there is another addition cohort, for example, like this one and this one and other. So that means like our the high astrometric noise might be a hint of like possible extended sources. And we are glad like we can use this technique to find a small separation dual AGN. And as you can see, there are some candidates showing the merger feature in the HST images. For example, this one and this one. So they should be the real dual AGN at smaller separation. And the separation here, as you can see, they are all like below like 1 arcsecond, which is good because we are trying to find some candidate which cannot be searched in the ground-based telescope. So you might be wondering, like, if we put our candidates on this plot, where will they be located? So those red circle and the red stars are our candidates. As you can see, they are all below like 1 arcsecond, and they are located at the unexploded region. So with those candidates, we can know like what the with those sample, we can study their property and know like at those smaller separation, is there any deviation from the control sample, or is there any like emission in other wavelength? So here it's very good because we have a new sample at high redshift and also smaller separation. And because this is an ongoing project, so we need to we also have like some work, future work or ongoing work to do. We can test if the astrometry technique really is the reason for high astrometric noise. If it is due to the astrometry technique, you should expect to see there's a correlation between the astrometric noise and the flux variation. So as you can think, if the flux variation is very large, you should expect to see the centroid will shift more. So it will lead to the high astrometric noise. Also with the dual band HST flux, we can reject the lens quasar or quasar plus star, because if it's lens quasars, their flux ratio should be very similar. And if it's quasar plus star, the star should have very red colors. And we can also fit do some Gaussian fitting using like point square function to fit the data. For example, like the bottom panel, and we can remove the emission from the central core and to see if there is other merger feature, as I mentioned in the HST images. So, besides the imaging, the HST images, we can do more. We can do the optical and near infrared spectroscopy observation to get the spectrum of individual core, and we can study the nature of each core. So we have several ongoing observations. For example, Gemini, GMOS, and Hubble, and also the Gemini Juniors. So those will help us understand if those two core are real binary or real length, or just the quasars plus star. Because with only the HST imaging, you can roughly guess, but it's not the 100% sure they are a real binary or length or star. So we need to take the spectrum of individual core, and we can also use those spectrum to, for example, measure the black hole mass or calculate the Eddington ratio and understand the physical property of the individual cores. We also have other like multi-wavelength observation for those candidates. And for example, the VLA or Chandra, and we can identify like radial core. And because like with the radial interferometer, the good thing is it will provide us the high angular resolution. So we don't need to worry about like cannot resolve those cores. So those multi-wavelength observation can also help us to see if there is any merger-induced effect in the X-ray or the radio. Okay, so here I want to conclude my the two projects with those takeaway points. So for the first periodical quasars candidate, we have the 20 years multiband light curve, which is a very long light curve, and help us to identify any periodic signal. And we have found like 5 candidates. And in our analysis, we find the Doppler boosting are highly unlikely. And we also think for the other physical interpretation, we also think the radial jets and the tilted accretion disks are not the possible scenario. However, the QPO is still possible. And the future LSST will provide us more quasars and also extend the time baseline by 10 years. And for the second project, we call it Vodka. And is a new astrometric technique to find the unresolved dual AGN, and it can provide us a new sample of finding the dual AGN or lens quasars with a separation smaller than 1 arcsecond using Gaia. And our Hubble follow-up shows a very high success rate, so which is good. And it will become a first large sample for the sub-arcsecond dual AGN at high redshift. Our ongoing spectroscopy observation can help us determine the nature of each core. So with those, I am happy to take any questions. Thank you.
Any questions for Tony?
For your periodic quasars, you show that they are close to AGN sources. So are there phase-on sources, and is the inclination affect your result?
Yes. So if the periodic signal is due to the Doppler boosting, the inclination will of course affect your the amplitude you see. Like as you can see, like if it's AGN, you should see like large amplitude if it's phase on. However, like it will only affect the amplitude, but it will not affect the, for example, the test here, because the amplitude are divided by the amplitude in another band, so it's already considered in the test here. Yeah. And our candidate also shows like the Doppler boosting is not a very possible scenario. Yes.
If we look at the diagram shows I don't know what you call it. The diagram of the first and second.
The diagram of the first.
This
one, or the periodogram.
Not this one. No, this one way swing.
This one.
No, the largest one there. Yeah, this one.
Yes.
What is the with the star?
Oh, you mean?
Yeah.
You mean this one?
Yeah. No.
Oh,
yes. The star is a very good success rate in getting the special samples you're looking for. In this case, and this is really the stars in both diagrams shows the letters in the other stars are very they're quite difficult to fit with linear way or anything.
Yeah. So yeah, I mean we are not trying to find any linear correlation between two parameters. So here I'm just showing the differences between our sample and the previous survey. Yeah. So here I'm just showing our the magnitude. Our candidates are much fainter than the previous candidates found in other surveys, and their black hole mass are smaller and at high redshift. Yeah.
Why is that? Why is why in this sample this particular sample you said you're able to see much deeper than the rest?
Oh yeah, because our the data we use are from DES and SDSS. So the DES is the 4-meter telescope, so which it has a large mirror, so it can observe more deep fainter sources. So in the previous, for example, the PTF or Pan-STAR, they are using the smaller telescope, so the sensitivity is not like deep enough to observe, for example, the those candidates down to 20 to 22 each. Yeah. Yes.
Okay, good. Two questions.
Okay.
First, you mentioned about at the introduction about the parsec problem.
Final parsec, yes.
Yeah, final. But those are all far from the parsec scale. It's all 100% or kiloparsec separation.
Right. Yeah. So for the second project, like they are around the kiloparsec. But for the first project, we are trying to find, like if they find the milliparsec scale candidates. So if
But did you find out? What's those kind of separations? Can you tell? Did you tell?
So for those candidates, it's hard to tell because their separation are too small. So you cannot use like the direct imaging to check if there's real like two cores. So we need to rely on those like indirect methods, so which is still uncertain. So we still correlate like candidates or yeah.
The other question related to this is that the condition is that they have to be the AGN. Both have to be the AGN. Well, even one have to be the AGN.
Right. Right.
And,
So yeah.
If two binary supermassive black hole binary at the parsec scales or smaller separation, can they feed them to be the AGN?
You mean for the kiloparsec scale, like, or the parsec scale?
Parsec or smaller.
Yeah.
Can there something can go in? Again, that to make it parsec or smaller, something
Yeah. So
have to go out. Then
right. So yeah. So yeah, I mean like it's hard to answer this question. I mean yeah, because I'm not like doing the. So if those candidates are real binary, so their separation are around like milliparsec if they are real binary. If so, they will tell us like maybe they already overcome the final parsec problem, and we need to like have more like theoretical explanation for like how they can carry out the angular momentum. I believe like now lots of people have like come up with the solution. For example, the gaseous like accretion, they will carry out like the angular momentum or like asymmetric like orbits such as, but I'm not doing simulation, so I'm not familiar with those theory, but I believe people will find a way to explain this. Yes.
But the only thing I care about that it was I think
Yes.
taking out is easy, but to feed a black hole is I'm not sure. With
Oh,
this
right.
level.
Right. So I believe if let me find. So if at this scale, yeah, I'm not sure if they need to both to be like active or just one. Yeah, I still need to think about it. Yes.
Good. Any other questions?
Yeah. We're soon going to have 1.3 meter telescope.
Mm-hmm.
It's very fast response. Would that be any use to what's the use of for the astrogalactic?
You mean which telescope?
Astrogalactic telescope. Well, the 1.3 meter telescope.
Yeah.
So what are you going to use that for? I think? For
Yes.
in the astrogalactic.
So I believe because we also need like a large field of view. So for example, like the DECAM has 3 square degree field of view, because we also, besides the high cadence, we also need like large sample to search the possible periodic signal. So if if the telescope you say has a large field of view, maybe we can consider using this.
Any other comments, questions?
If still time. Sorry, one more. To make the Doppler boost,
Right.
it's a separation needed. It have to be really close.
Right. You mean
Doppler boosting.
right? Yes.
Have to be really, really close.
Right. And so the separation should be like the same as the separation I estimated here. It's around like milliparsec. Yeah. Yeah, because their period is around like the rest frame period is around like 1 to 2 years, and their black hole mass is around like 10 to the 8 to 10 to the 9. So if we just use like a simple Kepler third law, and the separation will be around like milliparsec. Yeah.
Good. Any other final ones? Okay, if not, let's thank Tony again.